In 1962, a chemist walked into his lab at the University of British Columbia with an idea that his colleagues would have thought was absurd. He was going to react xenon, an element that every chemist knows is completely fundamentally chemically inert with one of the strongest oxidants out there, all because he had seen something that made him wonder, what if? His experiment produced a bright orange solid that had never existed before in the history of the universe. One moment and 60 years of chemical dogma was put into question. This is the story of xenon, an element that is pretty rare but is also hiding in plain sight, an element that conventional chemistry wisdom says is boring, and an element that today is used to push spacecraft across the solar system. Hello and welcome to Meet the Elements, the series where I look at the stories of humanity through the lens of the periodic table. Today we're talking about element 54, xenon, a surprising element involved in some fascinating science. But first, if you haven't already, make sure to subscribe and hit that notification bell so you don't miss future episodes of Meet the Elements. And now that you've done that, let's talk about xenon. Xenon might not be a name that means that much to you. It's a noble gas, it sits over there on the right side of the periodic table, it doesn't do much, or so the textbooks say. But xenon has a story. Let's start at the beginning. And the beginning, like so many good stories with chemistry, starts with someone trying to push the limits of what they know. William Ramsay was the driving force of discovering and characterizing the noble gases in the late 19th century. He was a Scottish chemist who had already discovered argon in 1894. That discovery had revealed an entire hidden column of the periodic table, a group of elements so chemically unreactive that they had slipped through every chemist's fingers completely undetected. Ramsay wanted to find more of them. In 1898, Ramsay and his colleague Morris Travers obtained a sample of liquid air, intending to study the gases that make up the atmosphere. The idea was straightforward enough. Cool air far enough that it liquefies, then slowly warm it back up. Different gases will have different boiling points, so they come off at different temperatures. You collect each fraction separately, analyze it, and see what you've got. This is a process called fractional distillation. The most volatile gases, the ones with the lowest boiling points, come off first. The heavier, denser gases stay liquid longer and come off last. At the very bottom of the distillation, the heaviest of everything remaining, they found a new element. They named it xenon, from the Greek word for stranger or foreigner. It makes up only about 87 parts per billion of the atmosphere. You're breathing it right now, an amount's too small to register without the most sensitive instruments. And if you manage to isolate it, what do you have? In 1898, what you had was an element that, by every chemical test available, would not react with anything. The noble gases were understood, through atomic theory, to have completely filled outer electron shells. No unfilled shells meant no tendency to share, donate, or accept electrons, which means they don't react. And this brings us to Neil Bartlett and his revolutionary discovery. Neil Bartlett was a young chemist working at the University of British Columbia. Trying to get a noble gas to react wasn't even on his agenda. What he was working on, though, involved the powerful oxidizing agent platinum hexafluoride. And when I say powerful, I mean powerful. It is amazingly good at ripping electrons away from other substances. It will even oxidize water. It's not something you handle carelessly. And in the course of his research, Bartlett made a fascinating observation. He found that platinum hexafluoride could react with molecular oxygen, O2, to produce a new compound, dioxygenyl hexafluoroplatinate. Now that probably sounds like nothing to the layperson, but this is where Bartlett stopped and thought about what was actually happening. To pull an electron away from molecular oxygen and turn it into an ion, you need to overcome the molecule's ionization energy, the amount of energy required to remove one of its electrons. Bartlett looked at the ionization energy from molecular oxygen and noticed it was only slightly lower than the ionization energy of xenon. Oxygen's first ionization energy is about 12.07 electron volts. Xenon's is about 12.13 electron volts. So if platinum hexafluoride is powerful enough to rip an electron away from molecular oxygen, why couldn't it tear off an electron from an atom of xenon? Convention said noble gases couldn't react, but Bartlett had the numbers. And when Bartlett reacted the two substances, an orange-yellow solid formed, a visible, tangible, real compound, and a xenon compound at that. The first noble gas compound ever deliberately synthesized. Bartlett published his findings in 1962 in the journal Proceedings of the Chemical Society. Of course, the original composition Bartlett proposed was later revealed to be more complex. As it turns out, the chemistry of noble gas compounds is complicated, but the core finding was still undeniable. Within months, chemists around the world were trying to synthesize more noble gas compounds. Most of the next discovered involved xenon. By the end of 1962, xenon difluoride and xenon tetrafluoride had been made. What this discovery did, beyond the specific chemistry, was to remind the scientific world that it hasn't been done is not the same as it cannot be done. The idea that noble gases cannot react was evaporated by one experiment. So xenon served a pivotal role at a turning point in scientific history, but I want to end this video with one of xenon's most spectacular roles, one that puts it on the frontier of human exploration. Xenon is a great propellant for ion thruster engines, and ion thrusters are really cool pieces of technology in the world of spaceflight. So traditional chemical rockets work by combustion. You burn a propellant, and the expanding gases blast out the back, pushing the spacecraft forward. The force is enormous. Newton's third law. Big force in one direction, equal force in the opposite direction. But ion thrusters work on a different principle. Instead of combustion, you use electricity to ionize a propellant. You strip electrons from atoms, creating positively charged ions, then you use an electric field to accelerate those ions and eject them from the thruster. Now, the thrust produced is pretty small. You're not going to use an ion thruster to launch a rocket. Instead, ion thrusters are the most practical when actually in the vacuum of space. But where they excel is efficiency. A key metric here is something called specific impulse, a measure of how efficiently thrust is generated from a propellant. Chemical rockets are powerful but relatively inefficient by this measure. Ion thrusters, on the other hand, can achieve specific impulse values upwards of 10 times higher than chemical rockets. For the same mass of propellant, an ion thruster can produce more total change in velocity. But why use xenon specifically? Well, a few reasons, and they actually connect back to the chemistry I was talking about earlier. First, xenon atoms are heavy, with an atomic mass of around 131. Xenon is one of the heaviest noble gases. For an ion thruster to produce meaningful thrust, you need each ejected ion to carry as much momentum as possible. Heavier atoms means more momentum. Second, xenon is relatively easy to ionize. Its ionization energy is low enough that creating xenon ions doesn't cost more energy than necessary. The thruster doesn't have to work too hard to pull an electron off a xenon atom. Third, xenon is mostly chemically inert. More or less what's happening when you run xenon through an ion thruster is this. You're ionizing it, accelerating the ions, and ejecting them. The xenon itself isn't reacting with anything along the way. It's not corroding the thruster wall, it's not fouling the propellant lines, it's not reacting with any other gases. A noble gas makes a near-perfect propellant precisely because of the property that made scientists ignore it for so long. It doesn't react. So that's xenon, found in the last bit of boiled liquid air, declared forever inert, then found to actually react with incredibly strong oxidizers, and now propelling spacecraft out into the solar system. What's great about xenon's story is the way it rewards patience. Ramsay found it by being meticulous. Bartlett discovered its hidden chemistry by being sharp enough to think about the math rather than trusting a consensus. And now engineers are using it to explore the solar system beyond our own planet. Thanks for watching, and don't forget to leave a comment suggesting future elements for me to cover. And if you want more tales from within the periodic table, make sure to subscribe so you don't miss the next episode of Meet the Elements.